Okay, so this is the fourth part of our introduction to pseudospectral methods. We've been looking at periodic functions, problems, PDE problems with periodic domains, and we've looked at Fourier pseudospectral methods. We looked at the viscous-Burgers equation as a one-dimensional problem, and so now let's look at two-dimensional transforms for 2D problems. Once we've done 1D and 2D, extending to 3D is straightforward. So our 1D basis functions were e to the 2 pi I n x over L. Now in 2D, we have the product of 2 pi I n x over L x and 2 pi I m y over n y. So we have physical space x, y, and we have spectral space indexed by modes n and modes m, which are different wave numbers in the x directions and in the y directions. So the inverse discrete Fourier transform and the discrete Fourier transform are given as shown here. So they parallel what we had in 1D, so you can see positive and negative. We have normalizing factors 1 over n and 1 over n. We have now nx in the x direction and y in the y direction. We have our sums in the Fourier indexed wave numbers, again go from n over 2 plus 1 to n over 2 for both n and m, but for j is in the physical space, j goes from 0 to nx minus 1 in the x direction, and k is 0 to ny minus 1 in the y direction. And we're not collecting the nx and the ny because we want to highlight that the term in brackets in a 2D transform is like a Fourier transform of Fourier transforms. So we have the term in brackets is a one-dimensional Fourier transform, and the outer sum is also a one-dimensional Fourier transform. So that's really convenient, and it makes 2D transforms a straightforward extension of what we've looked at for one-dimensional transforms. Now, notationally, I'm using n sub n and n sub x just to highlight the bounds here, and when I'm summing over a physical index versus a spectral index. But of course, the number of modes n is the same as the number of grid points x, and similarly for y, m, and y. So when we go to implement this, we'll notice that this this term in brackets is a one-dimensional transform. Now this isn't going to be a nested sum. This is going to be a sum, an inner sum, and an outer sum. So this inner sum is a one-dimensional transform. So for each x position j, each xj, we're going to do this one-dimensional transform where we're summing over y lines. We're effectively summing lines y. So if you imagine a two-dimensional grid, we're going to do an f of t and y, an f of t and y, an f of t and y, an f of t and y. We do that for each x0, x1, x2, x3. That's what this summation is. And when we've done that, we're going to have matrix C tilde Jm. And I'm writing tilde because I'm not quite there yet. We were trying to get to Cnm, but so far we've only converted the k direction to m. We haven't converted both the x and the y directions. So we're going to call this Cj, C tilde Jm. So we do a discrete Fourier transform for each value of x. And then once we have all of those, we're going to do another set of discrete Fourier transforms over the x direction for each value of m. Okay, that's a mouthful. But let's look at what it looks like in the code. So here we have two functions, f of t 2d and I f of t 2d. And for the f of t 2d, first we pass in our matrix U. We create space for the matrix C, and then we're going to loop over all the x points and then evaluate the c's as an f of t. So pretty simple. And then we're going to loop over all the m's and do the f of t over lines in the x direction. And that's it. And this thing gives exactly the same results as the scipy.fft FFT2, which is the 2D version of the FFT. So if you pass in FFT2, pass in u, you'll get the exact same thing as this function right there. And similarly for IFFT, it does the same thing. Pretty cool. So, and the cost, because these aren't nested, they're not, the cost isn't n squared. The cost is 2 size n loops. So it keeps things relatively inexpensive. Okay, let's look at derivatives. So if we take the derivative, again, here's u. If we take the derivative of this with respect to x, then this factor 2 pi I n over L is going to come down. And that's what happens. The 2 pi I n over Lx comes down. For higher order derivatives, we just have this will be to some power. We can simplify this to basically just taking, make it look just like it did in one dimension. So if you've got a two-dimensional grid and you want the derivative in x, say, then then just considering a line of u in the x direction and just take the FFT of that times this factor, and then the IFFT of that will give you the line of derivatives in that same direction. So it's pretty simple to apply this. And so if you wanted the derivative with respect to x at every point in the grid, then you'd evaluate this along a line at a given y, and then evaluate it along a line at the next y, and so forth. In other words, you evaluate it for a given y, you evaluate the FFT over all the x's. And for the next y, you evaluate the FFT over all the x's, etc. Where this uk is the array of u values at points in the x direction j for a single value of the y direction yk. Showing that this thing is the same as this thing is done on the next slide, so there's some details there you can follow along. The basic idea is we do something similar to what we did when we showed that the inverse was the same. So we're basically going to do a substitution. So I'll just take you through that briefly. We're going to do a substitution where we put in, we're going to insert the 2D DFT for Cn. So we substitute this whole quantity here into there. We substitute that in there. Well, we don't substitute it in there. We substitute it in here. So we take that whole Cn and we substitute it into this derivative function. And that's going to give us this nasty thing with 4 summations together. Before we do that summation, we need to change the little j to big J and the little k to big K to avoid clashing indices with the k's and the j's that are already in this term here. So you've got that. If you reorder the summations and then use xj over lx as j over nx, and similarly for y, that's what we've done here to get this. And then we've reordered some of the terms. So the sum on the far right here, this sum, when little k equals big K, this whole term equals is just e to the 0, which is 1, and you've got nm of those. And so that nm is the same as ny, and it cancels with that one right there. And so that's convenient. And then the sum over k, big K right here, that becomes a single term because we need big K to be equal to little k. And so everything drops out except for the when big K equals little k, so this becomes a single term. And that means we can we just dropped out 2 of these summations, which is great. Now we're back to this thing here, and we recognize that this thing is simply what we were looking for, which is the simpler version of this. So the inner here, we have, this is the discrete Fourier transform of u, multiply it by this factor, and take the inverse discrete Fourier transform. And all of this is done across all the x's for a given value of k. Okay, so that's the details. Okay, so now let's do an example. Let's look at the 2D heat equation. No source term. We can add that in if you want, but let's keep it simple. So we have the 2D heat equation. We'll assume a constant diffusivity. Gamma is 1. We'll use periodic boundaries, and we'll make the initial condition be just as a rectangular hat function. So 0 everywhere with like a rectangular zone in the middle that we've made equal to 1.0, and then we'll just evolve it in time. So here's the code. We'll make it rectangular, so Lx is 2 pi and Ly is 4 pi. We'll do 20 points in x and 40 points in y. Gamma, the diffusivity is 1.0. We'll run it for 1 time unit, and we'll output 31 times. Set up our grid. And then, as usual, we're going to do a method of lines. So we need the rates, which is the right-hand side function, this whole thing. And to do that, then, when we come into the rates, we want the derivative in the second derivative in x and the second derivative in y. And then we'll form the rates as the diffusivity times the derivative in x and y, and then just return that. Now we have to reshape it, so when it comes in, it's a one-dimensional array. So like 0.1, 2, 3, 4, 5, 6, 7, 8, 9. So we need to stride that it's been strided into a one-dimensional array. So we'll recover our two-dimensional array for convenience of presentation. So we'll just reshape the array. And then once we compute the rates, we'll reshape them back to the one-dimensional array. So that's just shown here. In other kinds of codes, you don't have to do the reshaping. You can index as needed. Okay, and then the right-hand side's these derivatives. So basically, we're just computing the second-order derivative. And for that, I'm doing it rather than just do the two-dimensional FFT, which we could do. I'm just showing it using this formula right here, where we're doing that over a for loop. So for each value of y, we're going to compute the derivative in lines of x, and in each value of j, we're going to compute the derivative in lines of y. So we have the IFFT of 2 pi I n over L squared times the FFT, and again we'll just keep the real parts. And we need this array of n's and the array of m's, just like we did before. So we create 0 to nx minus 1, 0 to ny minus 1, and then we shift it by moving them all so they go from minus nx over 2 plus 1 to nx over 2, and similarly for y. Now, so again, for a two-dimensional PDE, there's not a lot of code here. All the action happens really in these lines right there. And then the rest of this is just the supporting cast, creating the grid and making the arrays and whatnot. Okay, now we have a finite difference version. We'll just do central differences on this. Again, we reshape our array, we make some index arrays, and then we do the central difference in x, central difference in y, reshape it for output, and then we can solve the problem by feeding it to ODE int with some initial condition, and then or reshaping the initial condition. The initial condition is just this sort of 2D hat function, and then you can see the result. And here's the solution. Visually, the pseudospectral method gives the same results as the discrete, the finite difference method. Here's our initial condition. You can see it kind of wash out as it diffuses towards as it diffuses towards some average. If we waited long enough, the whole domain would be colored the same shade at some value between 0 and 1. Okay, so let's stop there. So there's that'll conclude our discussion of Fourier pseudospectral methods, and we've shown kind of the background and theory for those basis functions. We've related them to the FFT and IFFT, or the discrete Fourier transform and its inverse, and we've seen geometrically what those functions look like, and then we've also solved it in 1D for the Viscous-Burgers equation, which was also nonlinear and which posed no special challenges, and also for the 2 dimensions, and solved the 2D heat equation. So the next set of videos will go through Chebyshev pseudospectral methods when we have non-periodic domains, and we'll see how those work.